Okay. So as we're getting started this morning, I wanted to point out something that I forgot to put into our weekly schedule, and I think that I just didn't realize the date of it in general. Our first Beyond Labs experiment is next week, and I didn't. I mean, obviously, I wrote our schedule and I wrote literally all the labs, but I didn't realize that by just looking at the titles of the experiments I created because of how I kind of incorporated it in. So we are using Beyond Labs as well as a couple other things. I was pulling up Canvas here so I can show you. I'm bringing this up for a reason also, I promise. Okay, so this is our experiment for next week. Right here is the PDF of that first experiment. I think this is the only one I included the PDF for because it was a newer lab for them, and so I don't know if it's in, like, if you have the software downloaded from the fall or the summer, I don't know if you would have this one. So kind of weird side note, but I included the PDF for it. Anyways, we're doing that Beyond Labs experiment. So because of that, there is a Beyond Labs preparedness assignment. I originally actually had it due today, but when I realized I'd forgotten to mention it, I pushed it to Sunday. So if you have the software downloaded, this will take you a couple minutes. If you don't have the software downloaded, it'll take you a few more minutes because you got to download it. The first thing is to download it. So there's a link to the installation guide. Here is the code, so you do not need to pay for it. That code will get you the software for free. Once you do that, you're going to open up the organic chemistry lab room, and you're going to click on synthesis in the top right corner. So that essentially just opens up the lab room. It doesn't open up a specific experiment. This is a picture I made last semester for my students, so I'm sharing it with you guys as well. It was my first time using Beyond Labs last semester, and so this is how I kind of worked it out the first time I used it. If you used Beyond Labs for general chemistry, this is going to look a little bit different because we're now in the organic portion of the software. So this is literally just a labeled diagram so that everything has a name. So you can, come back and refer to this as you're doing experiments in the future. But what you are going to click on is the lab book. So in the directions here, it says click on the lab book, type your name into the lab book, and then take a screenshot or take a picture showing the software with the lab book with your name in it, and then you're just uploading that picture. So really it's just a way for you to show me that you have the software downloaded. It's worth a couple points. It's easy. And then it also just kind of makes sure that you have that software ready to go. In the modules, in the very first one, so our class information module. Nope, I want this one. There we go. There's a Beyond Lab section. So this is the installation guide that is linked in that assignment. There's also a tutorial. So, I mean, you can look through that. You don't really need it right now, but you can look through it. And then this is that same diagram that I have linked. And then the installation code is also typed out right here. Beyond Labs does have their own YouTube channel. There's some good stuff on it. There's not a lot on it, but there's some good stuff. And then they do have a good help section on their website. So if you are running into tech problems, you can always email me. I am not the techiest of people, but I can reach out to people who are. But you can always reach out to them directly. I know that sometimes an email coming from a professor is going to get a quicker response than an email coming from a student, though, because unfortunately, that's just the way it works. Okay. Questions for the Beyond Lab stuff or any schedule-y kind of stuff? Okay. All right, I think we're good. So we're going to continue with chapter 5. And in chapter 5, we've been looking at enantiomers. So a reminder, enantiomers are two molecules that are mirror images of each other that are not the same thing. So there's a picture on here of carvone, and we have the R carvone and the S carvone. And so we learned Monday. There's our chiral center. We have the R, we have the S. So the only difference between them is whether that group that's attached is on the wedge or on the dash. That's what makes them different. Notice underneath them that we have a melting point listed, we have a boiling point listed, and they're identical. Enantiomers have almost identical properties, which can be challenging because it means that it can be difficult to separate them. But they do have a couple things that make them unique from each other. And this first one is really important in pharmacology. So how they interact with other compounds. So I've mentioned a couple times, if you look at the paperwork that's part of prescription drugs, it will have a picture of the molecule, have its full IUPAC name. And most of the time it will have the R's and the S's, or cis's and trans, whatever enantiomer it is that you're taking. And that shape of the molecule, so whether we have wedges or dashes, is really important. I take a prescription daily for headaches. I literally, if I don't take it, I wake up with a headache every single day. And so I take a nightly drug for headaches. And the molecule that's in there is one specific enantiomer. One of the reasons that prescription and drug research can be really expensive is because if they figure out that the R enantiomer is the one that helps me with my headaches, then they have to figure out what the S enantiomer does. If the S enantiomer does nothing, it has no harm whatsoever, that's fine. Then they're just going to give you the two mixed together, and literally half of it's just doing nothing for you. But if they figure out that the S enantiomer is going to cause liver damage or seizures or something else, then they have to separate those two enantiomers so that you're only receiving the one that is causing good and not harm. How that shape of the molecule interacts with the different organs in your body, or the different cells in your brain, or the different enzymes, wherever it's meant to go, is completely dependent on whether we have wedges or dashes, and whether the things on those wedges or dashes are electronegative or electropositive, and so how it's being repelled or attracted. And so pharmacology kind of becomes like a big puzzle. It's really cool. The other thing that makes them different, and this one's just kind of a weird thing, but optical activity. So we're going to talk on the next few slides what this means, but they rotate plane polarized light in different directions. All right, so we got to define all that because that just sounds weird. So we got to take a trip back to the start of general chemistry. When we have light, it is made up of two types of wavelengths that are in, they're perpendicular to each other. Couldn't remember the word there for a second. And so in this picture here, the electrical portion is vertical, the magnetic portion is horizontal. And if we take light and we pass it through a filter, so that's what's happening here. This is the filter. When light's coming from the sun, from light bulbs, it's coming out in all different directions. And so if we put it through a filter, instead of getting all these different wavelengths, now we're only getting one direction of wavelength. And so as it goes through that filter, we're eliminating everything else. Okay, we're gonna keep going with that. Here's our next part here. So we're starting over here with our light source. This is just representing the light going in all different directions. Here is our polarizer or our filter. So now it's only letting, let me switch colors. That's kind of hard to see. It's only letting that wavelength through. So the one that's just straight up and down. This little gray tube right here, it literally looks like a cement tube. It's a polarimeter tube. So this is actually like a glass tube that would be full of our chemical that we're analyzing. So literally just full of liquid. As the light passes through that tube full of liquid, instead of being at a straight up and down direction, the chemical in that tube rotates the light. This is what chiral compounds do, or compounds that have chiral centers. And that was our definition right here. They rotate a plane of polarized light. And so that's what this picture is showing us, is as that polarized light goes through the chemical, it gets rotated. At the end of the polarimeter tube is a measuring device. It's showing us how far the light got rotated. So if it stays at 0, that means that it didn't get rotated at all. But we're looking at how many degrees the light got rotated. So we're going to look just down here at the bottom for a second. The little symbol over here, the alpha, this is telling us how much the light was rotated. So the alpha is the rotation symbol for this. The 20 and the D are telling us temperature and the wavelength. Not for us, not really important. This is the part we really care about. So notice that we have the two enantiomers of 2-bromobutane. We have the R and the S. They're going to rotate the light the same amount, both 23.1 degrees, but in different directions. So the S is rotating it 23.1 degrees in the positive direction, and the R is rotating it 23.1 degrees in the negative direction. There are other labels that we can give these right here. Whatever compound is rotating the light in the positive direction, we could also refer to it as the plus enantiomer. It's called dextrorotatory. So dextro means to the right. The negative is levorotatory. Levo is to the left. I don't think those are like exact translations, but the root words for left and right and dextro and levo are connected in Latin. So dextro plus to the right, all connected there. So this can also be written as a little lowercase d. And then with the R, the R2-bromobutane, because it's the negative one, we could have a little negative symbol here or a little L. Let's see, we talked about that. The middle part here is telling us that it's referring to this equation up here. So it's really just saying that if we change the concentration or that polarimeter tube, if it changes in length, then the rotation that we're measuring will be a little bit different than the standard rotation. So we could use that equation up there to connect the two or to compare the two. If we have a mixture of R and S, if we have an equal mixture of R and S, it won't rotate the light. So if we have our light going through and the S wants to rotate it 23 degrees this way, the R wants to rotate it 23 degrees this way, but we have an equal mixture of the two, they cancel each other out. And so this last little blurb down here says that if we have an equal mixture of plus and minus, then we will get no rotation. The very first word there in the front is racemic. So this is an important word. Racemic means that we have equal R and S, or we could say equal plus and minus, or now we could say equal D and L. All of those mean the same thing. We're just saying that we have equal parts of each of the halves. Okay, I have one more thing to say, but let me see what's on the next. Nope, I have space for practice. Okay, I do need to say it back here. All right, here's an important thing. We can figure out R and S by looking at what's attached. This is what we did on Monday. We ranked them by priority. We did our rotation. We can figure out R and S by looking at the molecule. To figure out whether it's plus or minus or D or L, this can only be done through an experiment. So if a molecule is the S enantiomer, that doesn't tell us if it's plus, minus, D, or L. That doesn't tell us either one of those things. We would have to figure that out through experimentation. So let me kind of just reiterate that, use our new language. If we have this guy and we have this. So here is what we know. This is our, I'm going to put everything that's given, our given information, in purple. Okay, that's our given information. Just going to put a little divider line there. Now, by looking at these structures, I can say that alcohol is highest priority, the hydrogen is lowest, the ethyl is second, and that methyl is third. So if we do 1, 2, 3, we're going to the right. I know that this is the R enantiomer. I can figure that out from our structure. And if that's the R, the other one has to be the S. I could figure it out as well, but really, once I know one, I know the other. I was told that this one has a rotation of negative 12 degrees. What is the rotation of the R enantiomer going to be?
The opposite, so positive 12.
Exactly, positive 12 degrees. So we could also label this one as the negative and this one as the positive. Which one can we label as levorotatory, or the little L? The S or the R?
S.
The S.
Good.
Will the signs always be opposite of each other?
Yes.
Okay.
Yeah, they will always be equal and opposite. So that if the S is levo, then the R is dextro. Dextro, I don't know if I'm spelling these right, by the way. Dextrorotatory. Okay, I'm going back a second because that looks real wrong. Dextro, nope, that was right. I'm looking at my notes to see if there's anything else. No, this was just to make sure we kind of get that separation, that language down. So if you were only given that structure on the test and that was all you were given and you were asked if it was plus or minus, the answer would be you can't tell or there's not enough information. I wouldn't give you a question like that, but I don't like those kinds of questions. They're not fair. But just so you know, that is only determined through experimentation. Okay, questions about the terminology at all? We're going to do, I did tell you there'd be some math. We're going to do math on the next couple slides. Okay. So if we have an equal mixture of R and S, or DNL, or plus or minus, however we want to phrase it. Then we have a racemic mixture, and the light won't get rotated. It would have a 0-degree rotation. If we only have one enantiomer, then it will rotate the light in the designated amount. So our last one was 12, right? Yeah. So with the last one we were looking at, if we only had the S enantiomer, it will rotate the light negative 12 degrees. This is referred to as enantiomerically pure. So meaning it only contains one enantiomer. It's also referred to as optically pure because we're talking about it rotating light. So these are the two extremes, an equal mixture or only one enantiomer. But what if we have a mixture that's not equal? So we're somewhere in between those two. If we're somewhere in between those two, that means we have a mixture of the R and the S, and one of them is in a higher concentration than the other. So this takes us to the thing we're going to calculate. Enantiomeric excess. This is the percentage of the higher quantity enantiomer. So there's an equation down here. We are putting the observed rotation. So this is what we would get from the experiment, divided by the specific rotation of the pure enantiomer. So this would have to be provided. This is saying that the S enantiomer rotates the light negative 12 degrees, but the mixture of the two is rotating the light 4 degrees. What is the enantiomeric excess? So the rotation will be in between the two. So the last one we had negative 12 and positive 12. Sorry, my fiance is walking by with something strange. The rotation will be in between those two numbers, positive 12 and negative 12. It wouldn't ever be higher than 12, and it wouldn't ever be lower than negative 12. It will be in between those two, and the sign will match the enantiomer with the higher quantity. So let me show you what I mean. We're going to do two practice problems with this, one just kind of like basic info, and then one with that actual equation. All right, so here is our given information. We have two enantiomers. The S enantiomer has a rotation of positive 40 degrees, which means that our R is negative 40. So we actually wouldn't even have to be told that. We could assume that based off of what we know from S. If the alpha rotation, so this is our experimental mixture of the two, if it is positive 20 degrees, what do we know about the mixture? So if we have a mixture of these two chemicals, the R and the S, negative 40 is the lowest it could possibly be. Positive 40 is the highest it could be. And then we have 0 right in the middle. So if we're at 0, this is a racemic mixture. If we are between, oh, that didn't quite line up, did it? Let's try that again. There we go. If we're between 0 and 40, so anything on the positive side, that means that the concentration of S is bigger than the concentration of R, because S is the one with the positive rotation. And if our rotation is in the negatives, then that tells us that the concentration of R is bigger than the concentration of S, again, because the R is the one that's in the negative. So if we are told that the mixture has a rotation of 20 degrees, so we're going to be here-ish, we know that the concentration of S is greater than the concentration of the R. We're going to calculate some concentrations or some, not like molarity concentrations, but some percentages on the next slide, but just kind of like the concepts, the basic information. Any questions about that?
This is like given information that we would get, right?
The purple is given information. The
Okay.
blue and the green is what we can figure out from that information.
Okay.
Okay.
Thank you.
Anything else? Okay, so that equation that was on that last slide, that enantiomeric excess equation, we're going to use that. So here's our given information. Oh, we're using the stuff from the last slide. So our last slide told us that the S was positive 40 and the R is negative 40. We have a mixture of the two, and the rotation is positive 15 degrees. And we are going to calculate the percentage of each enantiomer. All right, so there's our given information. Here's what we're told. I'm going to go back and show you the equation. Down here at the bottom, enantiomeric excess is equal to the observed specific rotation divided by the specific rotation of the pure enantiomer times 100. So let's figure out how to use this. EE, enantiomeric excess, is equal to 15 degrees divided by 40 degrees times 100. So 15 is the experimental observed rotation for whatever our mixture is, divided by the rotation for the pure enantiomer, which is 40. And I'm using the positive 40 because my mixture was also positive. So without doing any math at all, we already know that the percentage of S is going to be higher than the percentage of R because our mixture has a positive rotation and our S enantiomer has a positive rotation. So that's a really nice way to check your work. We know that S is going to be greater than 50%, and we know R will be less than 50%. So we already have that part done. All right, let me grab my calculator here. So I get 37.5%. And I'm going to put S right here so we don't forget which one that is. Now, what this number means is this is the enantiomeric excess. So the rest of the solution, 100% minus the 37.5%, don't trust my head to do this morning, 62.5%. The rest of that solution, the 62.5%, is a racemic mixture. So we want to figure out percentage of R and percentage of S. We actually haven't figured out either answer yet. Any idea, any thoughts on how we could get to our answer? Answers. My mouse. All right, here's what we're going to do. A racemic mixture means that it's equal parts R and S. So we're going to take that 62.5 and we're going to divide it by 2. And we get 31.25%. So here's how we can think about this solution. 37.5% of it is S. 31.25% of it is S. And 31.25% of it is R. So this portion right here is what made up the racemic portion, the parts that essentially are canceling each other out. So our final answer then for this is that R is 31.25% of the solution. S is these two added together, which is 68.8%. I was not consistent with significant figures there, but we don't really care about them in organic chemistry. Questions about that math, the numbers?
For when you did the equation, you used plus 40 because it was on the positive side, correct?
Right. So because our mixture was positive, I used the positive rotation.
Got it. Okay, thank you.
Any other questions about that? Okay. Back to our little flow chart here. We've talked about constitutional isomers. We've used the kind of umbrella term of stereoisomers. We've talked about enantiomers. Our new word, diastereomers. I think of diastereomers as our gray category, our gray area. So enantiomers are non-superimposable mirror images. They're mirror images of each other, but they're not the same thing. Diastereomers, look at this definition. It's just the worst. Non-superimposable and not mirror images. So they're not opposites of each other. Mirror images are opposites of each other. So they're not opposites, but they're also not the same thing because they're not superimposable. So they're this weird gray category. And I'll show you what I mean on the next slide, or as we look at pictures of them. But they don't quite fit any of the other definitions. So a new one was created. In order for a molecule to have diastereomers, it has to have at least 2 chiral centers. Now, if we have enantiomers, so down here, these are drawn out as enantiomers. We have a cyclopentane. Attached to it, we have a methyl and we have a bromine. And the relationship between structure 1 and structure 2 is that they are enantiomers. They are mirror images, but they're not the same thing. So we can see that they're mirror images if we picture like a little mirror right here. The structure 1 and structure 2 are mirrors of each other, but they're not the same thing. If we tried to put them on top of each other, the groups would be opposites of each other. Same thing with structures 3 and 4. They are mirror images, non-superimposable. And we often show this with rings because with rings, we can easily do the whole dash and wedge thing. It makes it easy to see. So we have the bromine and the methyl both on wedges. So these are both cis, or we have one of each. So these are both trans. Now, if we compare structure 1 and structure 3, the bromines are in the exact same position. They're both wedges. So when I think of diastereomers, I think of it as the gray area between something that's identical and something that is opposite. And what I mean by that is when we compare structures 1 and 3, the bromine half of the molecule is exactly the same. They're both wedges. The methyl half of the molecule is opposite. One methyl's a wedge and one methyl's a dash. So we can't label this relationship as identical, and we can't label this relationship as opposites. It gets a new category. They become diastereomers. And then the same thing is true with all of these other relationships. So 1 and 3, 1 and 4, 2 and 3, 2 and 4. We could do that same comparison between any of those, and their relationship would be diastereomer. So we're going to practice this with some drawing and some labeling. I'm going to draw just a stick version, no dashes or wedges. There's our molecule. We are going to draw all the stereoisomers, and find enantiomer pairs and diastereomer pairs. So I'm going to show you how to do this a lot easier than what it seems. We have two chiral centers in this molecule, where the chlorine is attached and where the bromine is attached. The carbons on the end aren't chiral centers because they have too many hydrogens. They both have 3 hydrogens. The carbon in the center isn't a chiral center because it has 2 hydrogens. So those are my 2 options, where the chlorine is attached and where the bromine is attached. When we have those bonds drawn as just lines, like I did in the original structure, that's not indicating any specific stereoisomer. It's just saying there's a chlorine and a bromine here. That's it. When we want to draw them as stereoisomers, we have to draw dashes and wedges because now we're indicating a specific version of this molecule. So literally, we just kind of treat this as, I want to say like a logic problem or kind of even like a statistics problem. We start by saying, okay, well, they could both be wedges. Or they could both be dashes. Or the chlorine could be a wedge, the bromine can be a dash. Or the opposite. That's it. Those are the 4 stereoisomers for this molecule. All we're doing is we are drawing our 2 stereoisomers, so where the chlorine and the bromine are attached, in every possible combination. And there's only 2 options each. Really what we're doing is we're drawing the R and the R, the R and the S and the R, and the S and the S. We don't have to know which one is which if the question's not asking for that, but that's literally what we're doing. We're just flipping them back and forth to switch from the R to the S. Questions about the drawings? Okay. The second half of the question says, find the enantiomeric pairs and the diastereomer pairs. So I'm going to give these guys some numbers just because it makes it easier. Enantiomers are mirror images of each other. So which pair of compounds are enantiomers? Which ones are complete opposites from each other? Would be another way to ask that.
1 and 2.
1 and 2. Perfect.
And then 3 and 4.
And 3 and 4. And that's it. Each molecule is only going to have 1 enantiomer. When we have diastereomer pairs, though, because they're going to be half the same and half opposite, one molecule can have multiple diastereomer pairs. Diastereomer. And it's going to be all the other ones. So if 1 and 2 are enantiomers, what's a diastereomer of compound number 1?
3.
Mm-hmm. And we can look at it to compare. So if we look at compound 1 and compound 3, the chlorines are both on wedges. The chlorine half of the molecule is identical. On number 1, the bromine's on a wedge, and on number 3, the bromine's on a dash. So the bromine half of the molecule is opposite. So they're half identical and half opposite. That's how we label them as diastereomers. We could do the same comparison with 1 and 4, but now it's flipped. The bromines are the same and the chlorines are opposite. What other pair are going to be diastereomers?
2 and 3.
3.
2 and 3, perfect. So on that one, our bromines are the same. Our chlorines are opposite. What else?
2 and 4.
2 and 4. So 2 and 4, bromines are opposite. Chlorines are the same. And I think we've matched up every pair, haven't we? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3. Yes, that is all of them. So every pair will fit into one of these two categories. Questions about that? Okay. I'm going to go back a slide because I forgot. Well, let me see if it's on this slide or not. It is not. Let me see if it. Okay, we're going to add it to this slide. The maximum number of stereoisomers that a molecule can have is 2 to the power of n. N is the number of chiral centers. So the molecule that's on this slide, the molecule that we just drew, both of those had 2 chiral centers. So 2 to the power of 2 is 4. So that's why both of these had 4 chiral centers. With these ones, I think with the dashes and the wedges, or even thinking of it as R and R, S and S, R and S, S and R, we get those 4. It can be pretty quick to see that that makes sense. When we have 3 chiral centers or 4 chiral centers, when we're getting to larger molecules, that can be harder to picture. I wouldn't put something that big on the test because it honestly would just take too much time. It would take up too much of the test. But that is the formula that we can use to figure out how many stereoisomers there are. Now, the way that that was phrased, the maximum number of stereoisomers, it's phrased a little bit weird on purpose. If we have a molecule with a chiral center, we can call it a chiral molecule, or we can say that it has chirality. We used that term on Monday. If a molecule has 2 chiral centers and a plane of symmetry, oh, there's a typo there, not a plan of symmetry, a plane of symmetry, then it's actually an achiral molecule. So remember, A means anti or not. So what that's telling us is that if there's a plane of symmetry within our molecule and it has these chiral centers, it's not going to be a chiral molecule. So I almost think of this as like a molecule that has polar bonds, but because it has all that symmetry within the molecule, it's not a polar molecule, even though it has those polar bonds. So somehow in my head, I kind of connect those two kind of weird definitions. Here's the reason why. If it has this plane of symmetry, it's going to be superimposable with its mirror image. So here's our example here. We have cis 1,2-dimethyl cyclohexane. So both of the methyls are pointing up. We're looking at it in the Hayworth just because sometimes that makes it easier to see. This version is just showing the plane of symmetry in between. The left half and the right half of this molecule are the same. So if we draw the mirror image of this molecule, it looks exactly like the original molecule. So it is superimposable with its mirror image. So it doesn't fit the definition of chiral because it is the same as its mirror image. So it gets a special label, it gets a special name. It gets the label of Miso. A Miso compound is a compound that has chiral centers, but is not a chiral molecule. So in order for it to be Miso, it has to have 2 or more. Let me erase this circle. Squished myself in there. 2 or more chiral centers and a plane of symmetry. Again, we often show this with rings because it makes seeing that plane of symmetry really easy. to have that plane of symmetry, the substituents have to be the same. So notice in the last couple examples we used, I had a chlorine and a bromine. This one had a bromine and a methyl. Those two substituents are different from each other. If they were both bromines or both chlorines, then we would have a meso stereoisomer. So for this one, instead of having 2 to the power of n, instead of having 4 stereoisomers, it's only going to have 3. It's going to have the trans, both versions of the trans. So the, well, I'll just draw the other one here. So those two are enantiomers of each other. And then it's going to have the cis, but it's not going to have the mirror image of that one because it's the exact same thing. So we wouldn't draw the same thing twice. So when we have a meso compound, it's going to lessen how many stereoisomers we have. Okay, I'm going to draw a couple, and we're going to decide if they're meso or not. Okay, so we have 3 compounds. We want to decide if they are meso compounds or not. Remember, our rule is that they have to have 2 or more chiral centers, and we have to have a plane of symmetry. Do any of these stand out as meso compounds? Or do any of them stand out as being something that would not be meso?
Three.
Which category does number 3 fall into?
Miso.
So number 3 is not going to be meso. It definitely fits the first definition. It has 2 chiral centers, but it doesn't have a plane of symmetry. If we try to draw a little plane right there, the left side and the right side don't match because one of them has the bromine and one of them has a methyl. So they're not going to have a matching side to each other. So not meso because there's no symmetry in the molecule. So with that, number
2 is gonna be meso.
Yeah.
yes, a couple of you were saying it. Someone said it in the chat, and I completely agree. So number 2 has 2 chiral centers. There's our plane of symmetry. So this one is a meso compound. Now notice how I drew that plane of symmetry. It's literally cutting through the middles of those carbons. On number 3, when I was looking for a plane of symmetry, I cut through the bonds. It doesn't matter. You can go through atoms or you can go through bonds. As long as we're comparing the 2 halves, you can do it either way. What do we think about number 1? Meso or not?
Miso.
There's a vote in the chat for it to be meso also.
Oh, true.
Oh, it's okay. You guys are voting together. Anybody want to go against them? It's not meso. It's kind of a trick question. It actually doesn't fit the first category. It doesn't have any chiral centers. So I know it's drawn with wedges. It's drawn in a tricky way. But if we looked at what's attached at that carbon, the carbon that looks like it should be a chiral center, it has, you know, this larger carbon group attached to it. It has a hydrogen attached to it. And then it has 2 methyls attached to it. It doesn't have 4 unique groups because 2 of the groups that are attached to it are the exact same. They're both methyls. So this has no chiral centers. So just because it has dashes and wedges doesn't mean it has chiral centers, and vice versa. Just because something is drawn without dashes and wedges doesn't mean that it has no chiral centers. Those are just a way to show a 3D shape of a molecule.
Will we only find Misos in ring shape?
No, they do also, so if we, what was our other example? Okay. So the example that we used before had a chlorine and a bromine. If we drew that same example, but had 2 chlorines on it, that's a meso compound. We could draw our little plane of symmetry right there, and the left and the right would be meso. Seeing the plane of symmetry in a ring shape is a lot easier because it's locked in that form. So it's often what's used as examples in practice problems, but meso compounds do exist in chains as well. So let me add a little meso label down there. Any other meso questions? Check our time here. I think oh yeah, we're okay. Okay.
Yeah, quick question. On example number 3, if instead of bromide we have a methyl group, would it be meso?
Yes, it would.
Okay.
Yep. Or if we had 2 bromines, then it would be, yeah.
Okay,
So
thank you.
it has to be the same compound in order for it to be Miso, and then I have a line of symmetry.
Yes, because in order to get that symmetry, those 2 substituents are going to have to be the same.
Okay. Thank you.
You are welcome. Would number 2 be meso if there was another substituent? Oh, that's a good question. Okay, let's see. Let me erase some stuff just to give myself some space. So if we had something else right here, let's just put a chlorine right there. This would still be a meso compound because we would still have that plane of symmetry right there. If, though, we added a chlorine right here, it would no longer be meso because it doesn't have a plane of symmetry anymore. So as long as wherever that extra substituent is added keeps the molecule being symmetrical, then yeah, it would still be meso. This one would give us that 3rd chiral center, but it would definitely still fall into that symmetrical meso category. So we'll put my plane of symmetry back in there. And yes, that is a line of symmetry to answer the other question in the chat. Any other questions about the meso-ness? Okay. The meso thing, just kind of a little side note, it can be a little bit hard to see because if we are looking at it in chains, we do have to sometimes do some rotations. And so how this will show up on the test is going to be literally like this. You'll be given, I don't know how many compounds, maybe 4 compounds. And really, you're just going to tell me, is it meso or is it not? So it's not going to really get connected into a lot of the other concepts. It will be just kind of its own little standalone question, just so you know how it's going to show up. So like in another question, if I did a question like this and I ask you to draw all the stereoisomers, tell me which ones are enantiomers, tell me which ones are diastereomers, there wouldn't be like a meso compound thrown into that to throw you off. So just so you know how it will get incorporated in. Okay. Fischer projections. So Fischer projections. I feel like as an organic chemist, and I've talked to past students about this too, we end up kind of having a love-hate relationship with Fischer projections. So this is what they look like down here on the bottom. We draw them with this straight spine bond going from top to bottom. Hey, shh. And we normally draw them for biochemistry molecules. So both of the structures in that bottom right-hand corner are sugar molecules. They're carbohydrates. And the reason why we do this for biochem, or for specifically for carbohydrates, is because we can easily see whether those alcohol groups are on the left or the right-hand side of that chain, which allows us to compare two alcohols, because the difference between two molecules, two sugar molecules, is just whether one alcohol is on the left or one alcohol is on the right. And drawing them as a Fischer projection makes them really easy to compare and see the similarities and differences. That's why we like them. We don't like them because they're not an accurate drawing. And so when we have, I'm gonna take my chair apart here. So we normally, let me do all my adjusting here for a second. Okay. We normally look at a molecule like this. So the black part of my molecule, my carbon chain, is a nice zigzag. The reason why we draw molecules like this and we draw dashes and wedges is if we look down one of those bonds, so Newman projection stuff, all of those substituents, or whatever, mine are red and gray, whatever they are all staggered from each other. So this is an accurate representation of what's happening in the molecule because of electron repulsion, steric hindrance, angle strain. And so it's drawing them as zigzags, dashes and wedges, staggered Newman projections is accurate. Now, in order to rotate this so that it looks like a Fischer projection, we have to take all of those bonds, the black carbon bonds, and do this. So my molecule's floppy, it doesn't want to do that. We are putting them in a straight line, but carbons don't go in a straight line. So even though we just draw it as a straight line, what's really happening is that it's curving around on itself like a C shape. So it's essentially kind of trying to make a ring. Let me just make this shorter so you can see it a little bit easier. We'll do four carbons. I think will be a good one. All right, so here's my zigzag carbon. To make it into a Fischer projection, we are making it into this curved C shape. So this up here is the top of my spine, and then it's going around. And when we're doing this, if you can look right down that bond right in front of my nose there, those substituents are actually eclipsed with each other. So this is not an accurate way to draw it, even though it does let us see things in a little bit better way. All right, get back to my little screen here. All right, so there's my own personal opinions on Fischer projections, somehow what that turned into. When we draw that straight line representing the carbon chain, so the vertical line, it is a dash. So here's just our super basic Fischer projection for a 1 carbon chiral center. So it has an ethyl attached to it, a methyl, an alcohol, and a hydrogen. So this is the Fischer projection. If we were to convert that into dashes and wedges, but keep the same look, those vertical lines are on dashes, and the horizontal lines are going to be coming out of the page as wedges. So I think I mentioned this when we looked at this back in probably chapter 2, but I always think of it as all those substituents are reaching out of the page and hugging you. Another professor always described them as it wears a lot of bow ties, so it has the bow ties going down the spine. Obviously, whatever makes sense to you is the one that it's going to help you remember it, but it's a way for us to draw them in just a different perspective. Here's the good side of Fischer. It allows us to see stereoisomers really easily. So here's our structure. We have these two bromines attached to it. And so we could have both of the bromines on the right. Actually, let me not just put an R there. Both of them on the right or both of them on the left. And so because those two structures are opposites from each other, we know that they're enantiomers. Or if we had both on the right or one on the right, one on the left, we can easily see that they're diastereomers because this bromine's on the same side, so it's half the same. This bromine's on the opposite side, so it's half opposite. Half same, half opposite puts them into that diastereomer category. So again, it gives us that quick visual of how compounds are related. We are going to, okay. We're going to do one more Fischer thing. Here's my Fischer projection. Is this the R or the S enantiomer? So we have to be able to do that with Fischer projections. So we're going to figure that out. And then the second part of this question is going to be to draw the enantiomer. Both of these things are going to be easier than what they might appear to be. All right. Our chiral center is that middle carbon. And that is the way that Fischer projections are drawn. I'm going to go back up 2 slides. So notice in the sugar molecules down here that we do have this aldehyde at the top and we have this CH2 at the bottom. They're not part of that spine because they're not chiral centers. So this has 3 chiral centers. 1, 2, 3, 4, and the other one has 4 chiral centers. So again, we can easily see how many chiral centers the molecule has. Even if it has more carbons than that, we know that they're not included in that spine because they're not chiral centers. Okay. So 1 chiral center, it has that aldehyde group attached at the top, a hydrogen, a methyl, and an ethyl. So to figure out if it's R or S, our first thing is we need to rank these based off of their atomic numbers. So which of those groups is going to have the highest ranking? The aldehyde, hydrogen, ethyl, or methyl? Who's going to be number 1?
Would it be the alcohol?
It is going to be the group up here. It is an aldehyde, but yes, it will be the oxygen group. You are right. I knew what you meant.
Hydrogen's last.
Hydrogen's last. Perfect.
Ethyl and then methyl?
Ethyl then methyl. Perfect. Okay. Our second step was to put the lowest priority in the back, or kind of our shortcut for that is we just, if it's not in the back, if it's in the front, we figure out what it is, whether it's R or S, and then we just flip our answer. So with this, because our hydrogen is on a horizontal, that means that it's on a wedge. So if our number 4, which usually is a hydrogen, is on the horizontal, then we're going to figure out whether it's R or S, but our real answer is going to be the opposite because it's in that wedged position. And remember, when we're counting, we're ignoring number 4. So we're going to go 1, 2, 3. So what is this molecule? Is it R or S?
R.
Was that one of each at the same time? I liked the stereo. So, okay. We're going to the left right now. So we would be making a left-hand turn. This is our steering wheel. But we're going to flip that. So I know one of you was right.
Wait, how come we're flipping it again? Because of the
Because-
4, right?
Yes, because our lowest priority is on a wedge.
And it has to be on a dash.
Yes.
Okay.
So we would either have to kind of rotate this around in our heads in a structure, redraw it, or we just flip our answer. So what do we think? Is this going to be the R or the S enantiomer?
R.
R.
Good. Oh, what happened to my line there? That was weird. There we go. This is the R. So we're going to the left as an S, but because our hydrogen is pointing in the opposite direction from what we want it to be, or from how we should be viewing it, we're going to flip our answer to get to the R.
I did have a question in regards to the placement of the hydrogen.
Yes.
Is that like always, if it's horizontal, it's always going to be wedged?
Yes, that's just the rules of Fischer. Anything on a horizontal is a wedge, and anything on a vertical is a dash.
Okay, thank you.
All right, the second half of this question says to draw the enantiomer. So there's my Fischer projection template. Here's the easiest way to draw the enantiomer of a Fischer projection. We keep the verticals the same. So I'm going to keep my aldehyde up here. I'm going to keep my methyl down here. To draw the enantiomer, we flip the horizontals. So my hydrogen was on the right-hand side. I'm going to put it on the left. And then I'm going to put my ethyl on the right. That is the enantiomer of our original structure. And the way that we can kind of prove this to ourselves, the way that we can see it. 1, 2, 3. The order is going in the opposite direction. That's what tells me for sure that this is the enantiomer. I've flipped the direction of my substituents. And you only have to move 2 things. Always move the 2 on the horizontal. Questions about that? Okay. We talked about Newman projections in chapter 4 and chairs in chapter 4. These are conformations. Conformations can be switched between different, I was going to say between different conformations, but that's like using the definition in the definition. We can be switched between the different types. So meaning we can go from gauche to anti to eclipsed, because all we're doing is we're rotating a bond. Our single bonds have that free rotation. And so when we have these 2 different versions of the gauche conformation, they are technically non-superimposable mirror images. And there's a big but there, but they're not chiral compounds because they can interconvert between each other. Notice it has that equilibrium arrow in between them. We can go from having our 2 methyls, or the 1 methyl to the right or the methyl to the left, because it has that free rotation. The same thing is true with our chair conformation. So these are both in the cis configuration. They are mirror images, but they're constantly interconverting between each other because, again, it's just that bond rotation. When we're looking at R and S, they can't interconvert between each other because in order to go from R to S, I'd have to break this bond and break this bond and then put them back in the opposite spots. Switching between these conformations is just simple bond rotation, not bond breaking. So this slide in this section is kind of thrown in here in kind of a weird way, I think, but I also think it's important to understand the difference between the chairs that we've talked about, the Newman projections, and now these stereoisomers. So conformations can be rotated between one another, and then configurations, or our stereoisomers, would require bonds to be broken and moved around in order to switch from one to the other. So it's definitely more of a conceptual thing, but sometimes we need to hear that in order to either realize there's a difference or realize what that difference is. There's also some weird ones. So we're going to look at some of the weird ones. The weird ones are the title of this section. These are chiral compounds that don't actually have a chiral center. And the main thing they have in common is that they can't rotate. And so they're held in a fixed position, which will make them different than their mirror image, but they don't actually have that chiral center. So this is called BINAP. It has a real long name. When molecules get long names, we just give them acronyms though. And it has 1, 2, 3, 4, has 8 benzene rings, because that pH2 there, that means 2 phenyl groups are attached to that phosphorus. That's 2 more benzene rings. So because it has all of those bulky benzene rings, it can't rotate around that bond right there, that one single bond, because these 2 groups can't pass by each other. So because of that, there's 2 versions of this molecule, 2 stereoisomers, and it doesn't have any chiral centers. It has a special name, tropisomers. You'll probably never hear that word again, to be honest.
Not even on the exam?
No, nope. To be
Okay.
honest, nope. Allene is another one that comes up. This one might come up like later in the semester or next semester, because it's kind of a unique example. But when we have a carbon that has 2 double bonds, so going in either direction, that carbon is sp hybridized. And because of those orbitals, we have a double bond going above and below the molecule, and then another double bond going in front and in back of the molecule. And so we can't have rotation there because those 2 orbitals can't move past each other. When we have double bonds that are kind of back to back like that, they're called cumulated double bonds. We'll definitely use that word again. I'll remind you of what it means. I don't know how many chapters down the line, but we'll talk about that one again. But when we have the 2 versions of this molecule, they are technically mirror images. They're technically enantiomers, even though it doesn't have that chiral center. But again, it's because of that lack of rotation. We're going to look at a couple slides here on how we would separate these enantiomers. So we talked about that they have almost all the same properties. And so because of that, we can't separate them by distillation, like we talked about in lab this week, or by solubility, last week's lab. And so we would have to separate them through another way. And one of the most common ways was actually figured out by Pasteur. So we've heard his name probably pop up in other chemistry classes, biology classes. If we were in class, we'd be using Pasteur pipette, so literally named after him. But what he did was he reacted a combo of enantiomers. So it was tartaric acid. So tartaric acid is this compound, but with hydrogens attached to those oxygens. He reacted it with a salt to turn it into the carboxylate version of itself. So the hydrogens have been removed from the carboxylic acids, and in their place are cations, so sodiums and ammoniums. Now, Pasteur was, I think the way he did this is insane, but also we learned a lot from it. So what he did is that if he looked at these with a magnifying glass, like literally looking at the crystals, he could see a difference in their shape, like the way that the crystal needles were angled. And he literally separated them by hand with a pair of tweezers. Because once we turn them into their salt version, they do have different properties. We don't do that anymore. We don't separate them by hand with tweezers, but we do use that same basic idea. So here's our pair of enantiomers. We're going to react it with another chiral compound. And when we do that, instead of having enantiomers, we create diastomeric salts. So here are our original enantiomers. Notice they're now charged because they reacted with the acid on the compound. So the compound that we were reacting it with is the compound we were reacting them with is an acid. The original enantiomers, because they have the nitrogens, are bases. So now we have ionic compounds that are diastereomers. Our original enantiomers are the half that are opposites, and then the compound we reacted it with is the half that is the same. Diastereomers do have different physical properties, so they can be separated through solubility or polarity or distillation, depending on what's going to be the easiest. We can also use something called a chiral column, which means that it's like literally a glass tube, and you put your chemical on the top of it, and it's full of silica gel. So if you buy like a new pair of shoes or a purse and it has that little packet in there of stuff that absorbs liquid, it tells you not to eat it. We use that in lab all the time, and it goes through that, and as it's passing through that, it separates compounds based on their polarity. So our compound that is more attracted to the solvent is going to move through faster than the one that isn't as attracted to the solvent. And so we can separate them that way as well. All right. One more topic in this chapter before we are done. Let me check my time over here. Oh, I think we'll have perfect time. We have talked about cis and trans. Cis and trans, in describing an alkene, describing a double bond, is used to describe the relationship of the hydrogens. So we use this for di-substituted alkenes. So meaning an alkene that only has two things attached to it. When we're talking about substitutions or substituents, we aren't referring to the hydrogens. We're referring to the other things that are attached to it. So if we had a bromine and a methyl attached here, those are my two substituents. To decide if it's cis or trans, we're looking at the hydrogens. So the way I just drew that is trans. And if I drew it this way, there's my bromine, there's my methyl. My hydrogens are both on the same side of that double bond, cis. Now, if we don't have two hydrogens to compare, that means that we would have tri-substituted or tetra-substituted. We can't use cis and trans because we aren't comparing two of the same things. So we can only use cis and trans for di-substituted rings and di-substituted double bonds. When we get to something that has more substituents, we're going to use E and Z to give it a label. Z, these are both German terms. Z is Zusammen. And so the way that I was taught to remember it is Sie same side. So that tells me that the two things that are the highest priority are on the same side of the double bond. So that's what this little guy down here is telling us. So the two high priorities that are just shown in red there are on the same side of that double bond. And then the other letter, E, is Enantiomeric. I don't know German. I'm sure I'm not saying that right. But if it's E, then that means that our two high priority groups are on opposite sides of that double bond. the way we figure out priorities is the same way that we do R and S. So we are looking at atomic number. Now this is going to be easier than R and S because what we're doing, we divide our double bond in half. We're only comparing those two. We just have to say, is the hydrogen higher priority or is the nitrogen higher priority? Nitrogen's definitely higher in priority. And then we look at the other side. We have a carbon versus a fluorine. The fluorine's higher in priority. And then we say, if the high priorities are on the same side, it's Z. If the high priorities are opposite, it's E. So we're not numbering 1 through 4. We're just numbering 1 and 2 and 1 and 2, and then comparing the ones. All right, let me draw here. The tiebreakers that we talked about are the same. So whether we got to kind of keep going down the chain, but it's not as severe because we're only comparing 2 things and not 4 things. So just a couple quick examples here. So I think the biggest thing to remember, or the hardest thing that can be to remember with this, is you only want to look at half at a time. So if we're comparing hydrogen versus bromine, which one of those is going to have a higher priority?
Bromine.
Exactly. And if we're comparing oxygen versus carbon, which one has a higher priority?
Oxygen.
Exactly. So that molecule, would we give it the E label or the Z label?
E.
There we go. Questions about that first one? Okay, what about the second one? So I'm just going to draw a little divider line there. Oh, we have the same hydrogen and bromine. I didn't really mean to do that, but we did. Hydrogen and bromine. Bromine's higher. What about the other side? So we have an aldehyde on the top, we have an alcohol on the bottom. Which one of those is going to be higher priority?
The aldehyde.
I know why you're saying that, but it's not true. It is the bottom one. And remember, we have to look at it one atom at a time. So we're actually comparing the carbon versus the oxygen. So the oxygen is going to be the higher priority. Now, if we had a molecule that had an aldehyde attached and then an alcohol like that, so carbon versus carbon, at that first atom, they're tied. The carbon on the bottom is bonded to 2 hydrogens and an oxygen. The carbon on the top is bonded to 2 oxygens because we get to count that double bond twice and a hydrogen. So in that case, it would be the higher priority. But because the oxygen's directly bonded to that vinylic carbon, that double bond carbon, it gets higher priority. So the one that's on the bottom, this guy down here, is that E or Z?
Z.
Good. And then that top one would be E as well. I think that was my last slide. Just want to double check before I announced it. And actually, we're right on time. That worked out well today. So that is it for chapter 5. We're going to do a chapter 5 worksheet in lab today. So you'll have lots of practice with this. So I will see you over there on our other Zoom link in a couple minutes. I will hang out here in case there's any last minute questions, but that's it.
So, Professor, I have a question.
Yeah.
It's not on chapter 5. It's like more on worksheet 4.
Mhm.
I was working on it last night, And I'm just confused as to I'm confused on the Newman projections. Like drawing them. Like I understand like the bond line drawings, like and how they're like how they're set up with the eye and everything pointing to like where we'd want to start up, but
Okay.
I'm just confused as to like there were certain ones where I just didn't really understand on how to draw.
Okay. So let's see. Let me pull it up. Do you have a specific number that was throwing you off?
It's okay. There's one on page 6. I think it's the third one with the isopropyl.
Okay.
Next one, I think. Yeah, the third one right there.
This one right here?
Yeah.
Okay. So with the eye looking right here, we know that that's going to be our front carbon, right?
Mm-hmm.
And because the dash and the wedge are in the top position, I have my Y pointing up or going in the right direction. Does that part make sense?
Yeah, okay.
Okay.
I understood that. I just don't understand. I understand that the like the left part of the bond line is isopropyl structure.
So this is the isopropyl pointing down right here.
So that would be, so like if you were to number it from 1, 2, 3, 4, and 5, that would be like the number 1, which is going down, right?
Yes.
Okay. So then 3 would be the NH2 and then the hydrogen.
Yes.
Okay. And then
and then our back carbon has the methyl that's pointing up.
Okay, yeah,
and
the
then,
methyl, ethyl, which is going down, and then the hydrogen, the hydrogen would be with the ethyl too as well, right?
Yeah, so the hydrogen is on a dash, so it's pointing in the same direction as the hydrogen on the other carbon. They're both the hydrogens are on dashes for this one.
Okay, and then the other question I had was for the NH2 and the ethyl, would they have to be on exactly the right side, or would we be able to put them on the left?
It kind of depends on what the question is asking. So
Okay.
for this question, because you're asked to draw that exact structure as a Newman projection, in order for it to be a right answer, they would have to be on the right-hand side.
Okay.
If you were asked to draw this structure as gauche or anti or high energy eclipsed or low energy eclipsed or the best stable structure, then my suggestion would be to draw it in the exact way that it's given to you. So the way that it's in the answer key, and then rotate that back bond around to get it in whatever position you need it. So whether you need it to be gauche or low energy eclipse, whichever one, but you want to start with it in the same position and then rotate it to get it to whatever the question's asking about.
Okay.
Does that make sense?
Yeah.
Okay.
All right. Thank you.
You're welcome.
I'm so sorry. Oh, what time do you start your lab? Maybe I could just come during your office hours or something.
It technically starts right now.
No worries then. I'm assuming your link is just posted on the homepage.
It is. So I have office hours tomorrow and Friday.
Okay. I'll see if I can join you at one of those two. Thank
Okay.
you. Bye.
Bye. Jerry, did you have any questions before I log off? Okay.
It was something about a question on the worksheet.
On chapter 4?
Yeah.
Can we talk about it during the lab? So you could, when I do breakout rooms, you could always just kind of hang out in the main room and do it that way.
Okay, sounds good.
Okay. All right. I'll see you over there.
Thank you.